doesn't have to go 27. Does that make sense?
You're literally using literally using stellarium to draw straight lines and measure the Earth, and you're saying that somehow the speed that the star is moving is different than they claim, even though you're using their literal software.
Well, their software is based on a calculation that's linearizing it relative to the fictitious observer. The difference in reality, there could be a difference in reality. No one's ever attempted to measure it using the true positions. Everyone that uses stellarium in the globe, how they use it, references the apparent position at an angle, and then whatever angle they're observing it at, they subtract the amount of refraction for that angle, and they reference where the true position would be to define distances and all of those things. So that's all we're using it for, because they have a predictive model of where these things should be. And so an observer on a globe should see the occlusion occur, a minute and 15 seconds earlier, because the star doesn't have to traverse the full arc length, which would take 2 minutes and 29 seconds. And you could verify that by, just looking at the angle and then the time and then playing it out and seeing when they line up.
Isn't that a good validation?
And another thing about, using stellarium real quick, that's why we add the arc length back to check. That's why we check from the peak. We're using that as the independent reference to check from for us.
So you made a comment then, Alan, I don't know if you can hear me or not, about the...
But yeah, to kind of end on that, I guess, would be what we see optically isn't the same as where things reside in 3D space. And so by using the occlusion timings, we have a reference to an elevation angle of when an object was occluded, and it comes out showing flat Earth.
And that's based on you claiming that the mountain can't be refracted because the refracted position can't occlude a light.
Well, no one's ever shown a mirage blocking a light source, and it's pretty common knowledge that a virtual image doesn't have actual light rays emitting from it, so it can't cause interference from another light ray. So,
okay, but the light source could be in an apparent position, and you could be drawing a line your line could be incorrect.
I don't necessarily disagree, but what we do agree on is when the star isn't visible anymore, it was occluded. So we can make references to where they say the light source was at that time. And if the light source was closer to our angle to the peak, then the Earth was flat. If we're above the peak by the drop over distance, then it would be a globe.
But if the star can be refracted, then it can occlude at a refracted time, just like a fish can swim behind something that's actually not swum behind yet because you're seeing a refracted position of it.
I don't necessarily disagree, but what if the refraction amount value was spherically integrated to the difference in elevation between us, and any observation that was made, I took out my original prediction of drop and added it back in, and then we just had the same baseline.
Then you're just assuming stellarium to be accurate again.
No. That's not what that would imply. This is a separate situation, right? Because they have a specific correction, right? They're saying that there is refraction. We're saying, okay, well, how much refraction is there? Well, when you take the temperature and pressure values for Pikes Peak, for example, it comes out to be 1 arc minute and 44 arc seconds, which is, let's just call it 2 arc minutes for simplicity. So there's 2 arc minutes of real world value, but then for their model, they integrate that over the arc length. So it changes that to a 13, which there's 13 arc minutes of drop over the distance. So by computation and spherical integration, they say, hey, if we add quote unquote refraction, then we can match your same angle, which is our flat Earth angle. That's a geometric argument, not a stellarium argument, because the refraction computation stuff, doesn't it's made up for the entire system or whatever. So it's not just for the stars.
So that refraction, Alan, and the spherical integration,
So, like, if I was trying to introduce a magic correction in every measurement difference, and it just so happened to be the exact amount that I said that I should have, made the measurement by, you would be like, you would be very
If you got
suspicious.
Daza
I'm sure,
turned down,
right? You would have questions,
Daza, that
and that's why we kind
Daza
of
keeps trying
disregard
to ask
the
questions, and you're
refraction
talking right over him.
aspect of it. And when we go through and show the
So
different
he's got me
strengths
turned down
in
too.
refraction, like it never holds to the degree in which they say there is.
Hold on, guys. Hold on. You guys
No,
gotta
I'm
stop.
I'm
No, not
talking
you,
to Q.
Alan.
Is someone here talking? Who?
Yeah, you got
Who is it?
Daza, Left Lane, and Wesley trying to chime in.
Oh,
The
yeah.
peanut galleries.
Yeah, no.
We don't need your
guys,
questions, bud.
Yeah, guys. Q-Op and I are having a discussion, so please hold your questions until the end.
It's a one-on-one, right?
I mean, fundamentally, and from a flat Earth position, this is not its true position. The light that it's coming that you're seeing, and you're drawing a straight line through the mountain. So I don't know how you're claiming anything regarding the shape of the Earth with this, honestly.
So even if it's not the true position, right, the calculated position within their model of where they're saying it is coming up flat. When we draw a straight line to where the star no longer is because it got occluded, it makes a congruent triangle for flat Earth. If you're not interested in using it or whatever, like that's totally fine. But it's a geometric argument. It's based off of the occlusions, which provide us obviously, like you said, that's not where the star truly is, but it gives us the reference point of where the closest approximation of where it last was to be a light source that's above an elevation that's either the flat Earth angle or the globe Earth angle.
You're basically all you're highlighting is that stellarium might be a little bit off, and that the stars are occluding a little bit later than stellarium usually suggests. But you're also admitting, you guys admit, and I have you guys clipped up admitting many times that it's close. You guys have gotten results closer to the globe method, the globe celestial theodolite method.
You can go through all of these measurements. Not a single one of them is closer to the globe intersection difference. The one that we talked about a couple weeks ago with S.E. Varley right here, where this value is 24, the globe predicts 22 drop over distance. Like the intersection difference, though, is the key part here because there's a specific arc length associated with the prediction. So when we look at this here, we have the central angle. That's going to be 8 arc minutes. The drop over distance is 4 arc minutes. The star ended up traversing 13 arc minutes in total. So it lingered even longer than what flat Earth would predict by 4 arc minutes, which gives us this difference to come out to be 24. That's this is a residual of the arc length being exceeded. This isn't a measurement of curvature within the confines of the actual arc length that predicted the drop over distance for it. So this is a mathematical artifact of the arc length being exceeded rather than the occlusion happening at the time that the angle, or at the time that it would have aligned for the globe geometrically. So there's actually no, like, whatever you think you have clipped up, you can go through all of these anytime you want. They're all available. Not a single one of them is geometrically closer to what the globe predicts. And the reason, like I just went over for that one that Jesse was trying to make a big stink over, is because the arc length was actually exceeded, and it just so happened to be exceeded by the amount that the drop over distance was. So it gave us the error of 24, and then it doubled the error for the globe because now the globe is now off by twice as much as what they would have predicted for the drop over distance. That's why when we look at this, let me go back real quick. So when we go back and look at this, we're off by 24, but they end up being off by 45 over the same arc length. Well, how'd that happen? What happened? Because the star lingered beyond 4 arc minutes over the original arc length. And we're doing the analysis over the arc length, so any residuals get divided up between us in that regard. So there's actually no measurement that confirms the globe in this at all.
I mean, you keep saying geometric, but like the occlusion happening later should be the geometric prediction of the globe, just based on what you guys claim the geometries are, which I don't agree with because the globe is reverse engineered from what we see. So we're seeing the same mountain. I still don't. I still
Okay,
like.
sorry.
I mean, it's pretty good. Like gymnastics and mathemagic you did from claiming to claim that the globe would predict it to happen sooner. But I don't think anyone here could steel man what the fuck you said when you tried to explain that. Especially, I mean, the main thing is that the geometries you're claiming are different, and you're claiming the mountain is lower on the globe. Yet your guys are assuming that the globe would have the occlusion sooner and that the flat Earth would have the occlusion later. So if you could try to explain that like with like in a scientific way and not like a mathemagic way, which you guys I got that term from you guys because I mean you guys kind of taught me how to basically debate you honestly because everything you said for last couple of years or whatever is about apparent positions and how they used mathemagic to basically ad hoc the globe. You guys are basically just cherry picking and doing some mathemagic to claim you're proving flat Earth, even though you're just really just getting people from flat Earth to believe more parts of the star map of the globe.
Sounds like you have a strong bias against what we're doing, and then you're kind of just saying different things after I speak. So you conflated the apparent globe angle to the geometric globe angle, which isn't which isn't what's measured here. And we talked about how their correction after the fact is just matching what we predict geometrically. So for them to even have a time to add refraction to, for there to be a lingering, there would first have to be an earlier occlusion time, which occurs because for the observer, they're already half tilted. The star in the sky only has to traverse half of the arc length to line up with whatever the
Yeah,
geometric angle
why are
to,
you
to
saying that though? I don't. You're just claiming that, but why?
that's that's the geometry of a globe. That's the point of showing this diagram. Oops, that's the point of showing this diagram that we had over here, talking about the.
The the
Hang on,
sky
hang on, hang
above
on,
the mountain is visible
hang on.
for on flat Earth and a globe. There's no uh,
They they
speed increase for being on a globe. It makes no sense.
Q up. Listen though, they only perceive half of the drop because for them the sky and the globe drop are 1 to 1. So the star only has to drop 13 arc minutes for the observer to intersect with the angle at 217. That's why. It's pretty straightforward. Okay. Just no.
You're
All
saying
right.
you're saying that the distance,
Yeah.
the geometric distance a star needs to drop is less on a globe.
The geometric distance that the star would has to traverse on the ground, essentially. Like if you were thinking about it in terms of like, how they say
Not
this.
traversing anything on the ground. It's
Well,
we are seeing a lens. We are seeing a hemisphere
just
lens. They are claiming
yes,
the hemisphere lens is a globe model. So
correct. So
where we
just
see it is
just
the
listen.
same. I don't. Dude,
Let me
this
walk
makes no
let me
sense what
walk
you're
you.
saying, dude.
I'm trying to walk you through this. Just give me a second. So as the star is angularly dropping, right, the globe lads would also say that the GP of the star is moving, right, across the surface of the Earth, 1 to 1, right? Because that's what creates the drop for the
Yeah.
observer. Okay. So the observer only needs to observe 13 arc minutes of drop before it intersects. Now, you could say that you don't like I'm just making it up or what have you, but you can just go into Stellarium and look at the true position when it intersects for that. It's literally the earlier timing. It's this time right here. It's oops, that's the wrong mountain. 1 second. It is 184204. It's in the geometry of that, right? Like if you wanted to understand geometrically why, it's because they only perceive half of it. They only need to perceive half of it. That's it. So saying like
Half of what?
half of the drop of the star before it intersects with the mountain peak. They're already tilted. The ground did half the work for them, essentially.
Dude, this is all like they're just what is that has the ground just because their globe is spinning doesn't make anything different about You're literally using
Chew up,
stellarium to do this.
chew up. Nobody said anything about spinning, man. Like
You just said the
it's
ground did half the work. I thought you meant like the globe like spun in the way or whatever.
elevation different wise. The difference between a sphere, an observer on a sphere and an observer on a plane, is they're always they only perceive half of the horizon. They only perceive, and the same applies to the sky. That's how they worked in the celestial horizon being at the equator, like relative to relative to an observer anywhere on Earth for the half of the hemisphere. That's how they relate it. So that's why it ends up being an earlier time. It's a geometric aspect of them being on a globe. Now, they say, well, there's refraction, and it just so happens that it's the exact amount of the drop over distance. So, which creates the timing difference for it to match what flat Earth predicts for the full arc length. So, if the star isn't dropping at 60 nautical miles per degree, like their model predicts, and it's lingering, then the flat Earth measurement, rise over run to the peak, is going to be substantiated in every measurement. And that's what happens. And then they come in with refraction and they're like, oh, but look, if I take out what I predicted as drop, then I can match your baseline. That's an apparent correction based off of assumed geometry that isn't present. And we only assumed one geometric, you know, uh, calculation, and we got the correct result. We got the result that's closer every time.
So can the atmosphere, different mediums of the sky, maybe of the ether, all these things, can they cause the occlusion to happen at different times?
I wouldn't disagree with that. And I've even shown at the beginning of a lot of the early Self Theo episodes, we would show Goose's measurement with the light source and adding the refractive medium and then showing the angle change at the occlusion time. It absolutely would. But the question is, how much refraction is there really? Because all they're doing is taking the actual amount of refraction that's measured and then spherically integrating it. So they can't actually know if there's that much refraction or not.
All right, so you're just basically just debunked your whole thing, claiming that the occlusion timing can happen in any time depending on different atmospheric effects.
Yeah, but how much? Does it affect it to the exact amount as what would be predicted as drop every time? That would be preposterous, man.
I have no further questions. I didn't think you were going to concede to that. That's not good.
It's our premise, dude. We open up shows with
Your
that.
premise
Like,
is that the way that you're timing this thing, drawing the line, can be affected by the atmosphere and other mediums, and it can be drastically it can be different than a straight line that you're hoping is 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 actually happening because you
the
want to
straight
use it
line
to
comes from
measure.
after the occlusion. The straight line comes from after the occlusion of where it once was. So, like, it's not the same thing as what you were just trying to say there.
Yeah, well, you said the occlusion timing can happen different based on different effects.
Okay, and you agree as well. So, do you agree then if we use spherical integration of the model that we're asserting that however much refraction is there is what's measured? Because if that's your assertion, you might as well be a globe lad.
No, I don't assert to know any of the mediums or claim that there's a geometric difference between the globe model and the flat. I don't claim that there's an optical difference. So the geometries are different, but they don't even really account for optics, and therefore, what we see is the same thing, but they just claim it's something different. So
That's our premise that the globe is an optical phenomenon. That what we see is optical. That's why we do the geometric comparison to the angle to the peak, for the rise over run to the peak and for what the globe would predict. So, because there's a difference in the actual geometry, but the optics, there wouldn't be. So I think I mean, honestly, dude, is there any other things you want to end on or whatever? Or was that pretty much it? You good?
yeah, I mean, I don't know what else, what more is there? You can't explain really like why the occlusion is happening quicker on the globe, you're saying it's because the globe geometry. I'm not sure how that affects what's above the mountain peak in the sky, which is all completely open to the air and is visible and is
Yeah.
happening at the same rate that we see stars occlude every day. It's pretty consistent. So it's not different on the flat Earth. It's the same consistent star pattern. You're claiming the occlusion can happen different because of atmospheric effects.
Dude, you're like reconflating different aspects of my position to make your argument, man. There's a specific rise over run angle to the peak, which is based on the time that it would take for the star to traverse the full arc length. On a globe, it doesn't have to do that. You can look at the intersection for what the observer-centric predictions are. Like, you might not be able to grasp what I'm saying at this immediate moment, but to say that I haven't explained it is, at this point, is
You've explained your reasoning, but your reasoning isn't really proving any any actual explanation for why the occlusion would happen sooner. It just doesn't. You didn't really say anything, honestly. You're just referring to the geometries and the math you're doing itself as the proof for why the occlusion would somehow happen sooner, which is still not even. It's like what is how much sooner? What's the discrepancy between like flat and globe, like as far as the time? Like it's
Fantastic question. So for flat Earth, we predict that for the star following sidereal time in 60 nautical miles per degree would intersect with the peak for flat Earth using rise over run at 1843.18. The star was occluded at an angle when it was at 233, so it was a little higher. So they got occluded a little bit before the full central angle, 2 arc minutes to be specific, which creates an 11-second discrepancy between prediction for flat Earth and what was measured. For the globe, they predict 1842.04, which is when the star's true position for the observer over that arc length would be intersected at 217. And that created a discrepancy of 1 minute and 3 seconds. Now, if you add our differences together, that is the expected drop over distance there. But the drop over distance of the arc length, so if you take this 13 arc minutes, it takes 1 minute and 15 seconds for the star to drop 13 arc minutes. If you go into stellarium at the observer location and put the star at 233, that'll rewind the clock by 2 minutes and 29 seconds. And 1 minute and 15 seconds later, as you press play, that star will have dropped 13 arc minutes for the observer, and it'll be aligned at 217, which will create a time of 1842.04. And then over here we have their refracted correction, which is the exact amount of drop over distance. So in other words, if there was no drop over distance, their time would be our time, and that's exactly what is shown here. So they have a geometric prediction that none of them want to adhere to. They would like to introduce a corrected position, which is just our position for what it would be geometrically, and they're trying to establish the optical conditions for the occlusion. But in doing that, they make the Earth flat. So,
I mean, it sounds like really good globe propaganda. Honestly, you're claiming the globe mountain is lower, and you're claiming the occlusions are happening later than than stellarium suggests.
I mean,
It's kind of
all the globe lads want to use the refracted position because it changes the timing difference. See, if you see the drop over distance here is 1 minute and 15 seconds for it to drop 13 arc minutes. Well, that amount of refraction, right, 13 arc minutes, is also 1 minute and 13 seconds. So, because it's a rounding error on the arc seconds, that's why the timing is slightly different.
they're just defending stellarium's accuracy. They don't really grant your
Right.
prediction or what your claim the globe should be. So
and no, and that's totally fine. But for them, not understand, like ignoring the geometric argument of it, is where their worldview has collapsed. Because to recover what the globe predicts optically, they have to remove what they predicted as drop over distance every time to match us. So we're geometrically flat, they're optically globing. So like even though they don't admit like the only globe lad to admit this or realize the significance of it was Mike. which is why he changed his position from being a globe lad to a flat earth lad. None of the globe lads want to acknowledge this because it leads to a conclusion. There's a clear geometric difference here. And when they use the apparent position, they recover our angle every time, which is geometrically significant. And understanding that aspect of it is a pivotal piece of of this. So
Yeah, I don't believe Mike's a flat earther.
well, it's totally fine, but can you believe that the rise over run to the peak yielded an occlusion that was 11 seconds off of prediction real time, and that the globe added a correction that matches our prediction that made it 10 seconds off by removing the drop over distance that they originally predicted? So irrespective of Mike's position, like do you grasp the significance of that?
I just don't grant any of the things you're the rise over run. I think is can be in apparent position. The mountain. I think the star is obviously in an apparent position. It's like the most extreme apparent position is the stars. That's why they appear to drop drastically from the sky. Like
Well, they linger.
this
It's not drop. They linger outside of what their model predicts. But go ahead.
well, I mean, their model predicts that you can draw straight lines to the stars, and you guys are doing the same thing. So
No, we're drawing a straight line to where an occlusion occurred based off of where their model predicts it should be. So we're not claiming that this is like the exact position or anything like that. They have a specific model that they're asserting describes the geometry of not only the ground, but the sky. And we're testing that through timing differences of occlusions. And what we found in every scenario, every occlusion matches what flat Earth predicts using rise over run to a geometric angle, not an apparent one. And when the globe lads come in, they add back the drop over distance as a refraction correction and say, look, it's the same for what we optically perceive.
can anyone besides Alan Steelman why the globe predicts? I mean, why the globe prediction is an earlier occlusion?
Not that I've heard of.
Or is it because it's like he's acting like I don't understand? It's like nobody understands what you're saying, dude, and you probably don't understand. That's why you can't explain it simply.
Okay. If you subtract 13 arc minutes of refraction, what position would the star be at?
For like, what kind of like riddle is that?
It's a straightforward question. If the star's refracted position is 219, right? There's 13 arc minutes of refraction. If you remove that 13 arc minutes of refraction, what position is the star for the observer?
From 219.
It'd be 206.
Okay, I don't know what that's like proving.
Well, for the observer, for that true position of the star to get to 206, it had to first get lower than 217, right?
Okay.
And the time that occurred was at 1842.04. That is the geometric position that we're comparing. And that's when it would have occluded. And
Why is it sooner on the globe?
Because the star only has to drop half of the arc length. It doesn't have to drop the full arc.
Does anyone know what he means?
Yeah.
Yes.
Yeah,
Can you explain?
there's no geometric intersection based on the angular height, right? So we're saying it only appears to get lower in the sky. It's not geometrically getting lower. So it doesn't occlude half the arc length because the Earth isn't curving up to meet it. On a flat Earth, that has to traverse the entire arc length, which is what we're seeing. And on a globe Earth, it would have to do half because the Earth is rising up to meet it. That's the difference. That's what half gamma represents.
Well, Shane agrees with you.
Well, even if he didn't, right, you could deduce this yourself by if you took 13 arc minutes of refraction and you didn't have that as the correction for the globe lads, right? So if you subtracted 1 minute and 13 seconds from the time of occlusion, you would be back at the geometric intersection angle that they would have predicted for the earlier intersection. So like you can verify this yourself and understand it. Whether or not they agree to it or who can steelman it is irrelevant. These are things you can do yourself to like it's straightforward. If adding this time difference makes it match the longer distance that it takes to drop, then
And there is no drop.
It would therefore follow that there would be an earlier intersection for this to be added to begin with. So it's like whether or not you understand the mechanism of why, it doesn't matter. It still occurs.
So I've got a question then. So if we were to do occlusion observation of Catalina from Oceanside, which is approximately 65 miles, Catalina has a 2,000 foot tall mountain range, and according to the trig on that, taking the tangent of it, it should still be something like 20 arc minutes or something like that. A silhouette that's 20 arc minutes, 2/3 of the height of the sun tall, of the silhouette of the island should be seen against the sun. Occluding the sun with its silhouette if the Earth was flat. But we know that even in June, when the sun is at the correct angle to be directly behind the island, you never actually see the island silhouette. You can't see the island at all from that location when you're standing on the beach 6 feet.
Do you have a question about like the presentation?
But no, my question is, shouldn't we, if what you're saying is that the refraction doesn't affect the occlusion, shouldn't we still see, when we're seeing the silhouette, when we're seeing the sun, shouldn't we see the island silhouette in the sun? We shouldn't see the full disk of the sun if the sun is directly behind the island, right?
Yeah, it should be similar to Mount Canigou, right? If that's what you're asking, it should be.
It should be like that. Yeah, it should be like Mount Canigou, because it's impossible for the refraction to somehow show you the sun, but not show you the silhouette of the island, which is occluding the sun, right? Which we know it should be occluding the sun, 2/3 of the sun based on the trig, right? So from Oceanside, you should be able to see the silhouette of Catalina against the sun, but we don't. We don't ever see that island.
I'll have to take a look. I've never heard of that.
Okay, I'm done.
Okay. Beast, did you say you wanted to say something about the occlusion timings?
Yeah, just the simple fact that, half of the arc length, what that means, queue up. So basically the observer to the mountain peak, that's the full arc length. So basically, for the globe, there should be a middle point to where it's cut off because of curvature between you and.
There's the curvature of the globe has nothing to do with anything above the mountain where the occlusion's happening above the mountain.
Curvature of the globe has nothing to do with it. Okay.
It does, because the position of the star as viewed by the observer is already going to be deviated. That's why the intersection occurs at 1842 relative to that arc length versus 1843 for flat Earth. So it only has to drop half. It doesn't have to. It never has to drop the full amount.
What full amount of the entire 360 degrees of a globe?
No, the 27 arc minutes of the arc length. So whatever the distance is between the observer and the peak, that's called an arc length. That angular amount, whatever it is, the globe or the star on the globe would only have to drop by whatever half of that angular amount is to intersect with whatever the peak would be every time.
Bro, it's honestly like you're saying you say the mountain is lower on the globe, yet you're saying somehow I really don't know what you're saying, but
because the star is already low. The star is already lower for the observer by half of the arc length, so it only has to travel half of the arc length to intersect with the peak for their angle. Like, even if you don't understand it, you could go into Stellarium and just like look at it and see the differences. It's like when it's aligned here versus when it's not aligned. Like this is
with refraction on or off.
with refraction off. And if you add refraction, okay, listen, Wesley, with refraction off, and then when you add refraction to it, what happens? It adds another 1 minute and 13 seconds back. So it adds the other half of the arc length back, and then the full occlusion time gets almost recovered, which is the flat Earth angle.
Yeah, but we see the star with refraction on. We see that where it is with refraction on. So why would you?
We've already went over how that's done through the refraction is computed through spherical integration of the arc length, which is in every scenario where there's an elevation difference between flat Earth and globe Earth, the refraction happens to be the amount of the arc length or greater than the arc length. I'm sorry, happens to be greater than happens to be the exact amount or greater than the drop over distance of the arc length, which is the half gamma, the half of the arc length. So
What's the OR for? Is the OR the inaccuracy?
no, when did I say or? What was it about?
It's just you're claiming you can measure the difference between flat and globe, which I don't know. It's like there's no real explanation for why they're different.
Earth
Because
curve.
the globe, we're not on a globe, which means they looked at the flat Earth and they made the globe model. So the idea that
Yeah.
they're actually different doesn't make any sense.
So
Stellarium is based on when things like where you see the stars and when they occlude and everything. So you guys are
no,
just finding
it's
out that
actually not.
stellarium might not be very accurate. As
It's
accurate as they wanted to.
it's actually not quite that, and most of your position is our position. What we perceive isn't the geometry of what is actually happening. And that's what the occlusions show. That's why optically it looks like this. That's why optically, when you reference their model, which is based on optics, we get this intersection difference that occurs earlier because they're making the observer centric prediction and comparing it to where it would be on a globe, which is changing their baseline to the horizon, which puts that star at a lower angle by whatever the drop over distance is to it. That's why it only has to, that's why it all hang on, dude. That's why it only has to go half. That's it.
Go half of what, dude? Does anyone know what he's saying when he says that?
Half of the half of the arc length, half of the drop in the sky.
No sense.
Does anyone besides the three people that are pushing this understand what that means?
Nope. The star is traveling down for both models at the same rate, and for some reason they use curvature.
And they're claiming the globe mountain geometrically is lower, so it would take longer to get to the globe mountain peak.
And they use curvature, but the
No.
not being blocked.
No. Hold on 1 second, Wesley.
By the mountain before curvature.
1 second, dog. We're not saying that it would be blocked by curvature. That's retarded. We're saying that the elevation of the observer is already tilted by whatever the drop over distance to the arc. Hang on, would be just stop for a second. It's already tilted by whatever the drop over distance to the horizon is for the observer. So the star only has to drop half of the arc length to intersect with the geometric peak at the end of the horizon there. That's why. And you keep changing things that you're saying about about our position, and it's really annoying because it's like you don't even know what our position is.